All right, sounds good. Okay, thanks everybody for joining Common Pitfalls in Machine Vision. My name is Lindsey Sullivan. It used to be Dragon, if that is familiar to anybody. I used to work in Minneapolis here, so if Lindsey Dragon's familiar, that was my maiden name. But I am a technical marketing manager at CCS America. So essentially, why do I, a marketing manager, get to talk to you? Here's kind of my experience. I started my career at Keyence here in Minneapolis, did sales for machine vision industry. Then when we moved to Boston, I got a job at CCS America. I was an application engineer. Then I became the application engineering manager. And when we had our first child, I was like, I don't want to travel. So they were like, why don't you do technical marketing? And essentially the goal of my new role is to take my technical expertise, my knowledge of what I saw when I was doing sales, and use it to help teach everybody kind of what I know, how to solve machine vision applications, and just kind of share the technical knowledge that not everybody can share. If you see me sitting throughout the presentation, it's because I'm pregnant, and when I practiced this standing up, I got really winded, and it was arguably embarrassing. So if I just randomly sit down, it's because I'm tired. But if you try and contact me after September, I won't get back to you till 2025. So, all right. So, what we want to talk about, what the point of this presentation is we want everybody to avoid the worst case scenario of a project getting derailed, whether it just doesn't happen at all, or whether it, delays other things down the line and you miss a delivery window or something like that. So what typically happens is customers call CCS and say, hey, we have this defect, we need to inspect it, we're kind of struggling. Can you, find a solution for us? About 1 to 2 weeks later, depending on how difficult the application is, we'll come up with the solution and we'll say, here's the report, here's how we would solve it, go forth. And more often than not, this is where it ends. People buy the light, they implement it and move along. The system is a success. Every once in a while, there's a feedback, hey, this actually won't work in our machine. There's a restriction, the light's too big, it can't be that close. And we say, oh, okay, thanks for sharing this new information. Another 1 to 2 weeks later, sometimes that makes it a lot harder. It does take 2 weeks at least. We say, okay, here's a new solution, maybe not as good as the first, but it should solve your application. And again, more often than not, we got all the information we needed and this moves forward. But every once in a while we have, hey, we actually can't implement that either. And then this is a bigger meeting, more people involved. Why is it, we're not getting all the information? What about this can you not implement? And a lot of times it just becomes that this application wasn't feasible at all. And so what ended up happening is, almost a month was wasted of our time, of the customer's time, because they spent a month not trying to find other solutions because we couldn't solve it. So essentially what we're saying is engineers kind of come to evaluations, they bring us evaluations with misconceptions and assumptions about what machine vision applications can or can't do or what they need to provide for us. So what I want to do with this presentation is stop this from happening. So, when we have these misconceptions, sometimes, as I just went through, we spend weeks on a project that was impossible from the start. Sometimes, that vision system is necessary and you have to redesign the system or rebuild it or modify your machine in some case, which will push a project back months. You'll miss a delivery window. It costs money. We want to avoid that too. And sometimes, we came across this a lot when I was doing sales. I would walk in and people would say, yeah, I got a machine vision system in the back corner. Somebody bought it and never worked right. It's been sitting there for 5 years. We don't want that either. We want the systems that we have to be successful. So what my goal here today is to just give you ideas, the expectations of kind of going into applications. What do we need for success? The misconceptions kind of break down into 5 categories of when to consider vision inspections, talking about scope and scope creep, the samples and conditions that we test with, previous application knowledge, and then seeing versus detecting defects. So on to all the misconceptions and why they're important to know. The first one and the most important one is I don't need to consider the vision portion until after the machine is built. And this is the first one for a reason. It is the highest consequence if it's not done right. If we can't put the light in that we need because there's too many restrictions, we just can't solve the application. And if the vision system is required, then you've got a bigger problem. So if we can consider vision from the start, we can prevent a lot of problems down the line. So what is it we need to consider and why do we need to consider it? First, we need to consider the clearance for the lighting and the camera. I do a lot of webinars kind of similar to this, and one webinar I've done in the past is talking about lensing and cameras and stuff like that. I'm not a lensing expert, but it's just a little intro to kind of the machine vision world. But one thing that I taught you on there is picking the right focal length lens for your application. If you're looking at the inside of a cup, you want a shorter focal length that can look down the sides of the cup. If you have a longer focal length, like 75 millimeters, you'll kind of have more of a telecentric effect. And instead of the inside of the cup being nice and long, it's going to be nice and short in your image. So if you have a focal length lens that you need, maybe an 8mm or 12, and you have a field of view that you need, that's going to restrict the working distance that you have to achieve that image. If you built your machine with a restriction that prevents you from using that working distance, you have to back it up. Your application's already harder than it needed to be. That same process and that same principle applies to machine vision lighting. When I do trainings, especially when I'm teaching people how to solve applications, my biggest takeaway is always check your light working distance. Always test that. How many times people have said, we tried a coaxial light, it didn't work, and I try a coaxial light, and I move it around, and I lift it up 6 inches, it works perfect. Almost all lights, I would say, yeah, all lights, the light working distance can make or break an application. And this example right here is exactly what I'm talking about. So we have a can that's got some height changes on it in our flat dome light, our LFXV series, which honestly, my favorite machine vision light. If you haven't checked it out, I recommend it. Anyway, as I get closer to the sample, it really flattens that image. I could read that code in the middle perfectly clear. I could read the Japanese on the edge. Very, very good image. But if my customer says to me, we can't let the light be that close, can you back it up? I would say, yes, we can, but the image will change a little bit. Now we're starting to see those height changes. If you're trying to read the Japanese text, it's not going to be as clear, as easy to read, but it might still be okay. And if they say, hey, I actually can't be that close either, you really need to back it up. Okay, now it's actually unsolvable. We could still read the code in the middle if that's all we're trying to do. But if we're trying to also look at the Japanese text, this solution wouldn't work. So what we really want is to give our machine the flexibility to solve the vision system the way it should be solved. Next, we want to consider the intensity and the ambient light. So machines, everyone is trying to make their machine go faster and faster and faster. That's the goal, more output. And LEDs used to be kind of a limiting factor, but there is so much technology now that LEDs are so bright, they shouldn't really necessarily be the limiting factor on your machine. So when you're building a new machine, if you know you want to get to a certain speed, which would require a certain exposure time, tell us, make sure that we know that, or to make sure that you're picking a light that's bright enough. Because worst case scenario, you buy a light, it's not quite, it's at 100% intensity, you're keeping up, but you don't have any room to grow. You can overdrive the light, put a different controller on or something like that, get up to, 4 to 5 times the intensity. But if your line speed is even faster than that, you might have to step up to our PF series, which can be about 3 or 4 times brighter than overdriving even. And that would require, figuring out the problem, trying other solutions, purchasing something else, and again, wasting money. But if in the beginning we knew, hey, this line could possibly get up to this speed, it's going to be this exposure time, I should probably just get the bright light now so I can grow and not have to make any changes when I'm eventually able to go faster by fixing a bottleneck down the line. Ambient light can also be a problem. It's not a problem with every application, but every once in a while it sneaks in there. So ambient light can create glare on an image. Everyone probably has come across, on a Tuesday your machine vision system works, but when it's sunny outside you get a big bright spot, something along those lines. The ways to remove ambient light, having a really fast shutter speed is kind of a good method. It will overpower the ambient light so it doesn't actually make it into your camera. The only light that the imaging system sees is what's coming from your machine vision light. If you can stick a bandpass filter on that, if you're using a red, green, or blue light, it'll just make the solution even better. But the tried and true method is to shroud. That will always just kind of remove the problem from the source. So not the biggest problem, not a problem that can't necessarily be solved, but if you can factor into your machine vision design, you're just removing one potential problem down the line. And last but not least, what to consider is presenting the part to the camera. If you know that you're going to have to do an inspection, you want to inspect the top, you want to inspect the bottom, you want to inspect a cylinder, you need to inspect all sides. Do you need multiple cameras for that? Is there room in your system to put multiple cameras? Do you need to inspect different, 8 different things on one part? Can you put 8 different cameras where they need to be? We also talk about fixturing. This is probably one of the hardest things to overcome, is if your fixture is blocking too much of the light. I've had customers have to actually send me the fixtures that their part is made in from the manufacturing along with their parts to make sure that I can solve the application while it's sitting in the fixture. And a lot of times, you know, the application requires a low angle light, but because the fixture goes so far up the sides, it blocks that light, and I actually couldn't solve the application, or we had to do it where, you know, we could really solve it this way, but most of it where we can solve with a bright light, something like that. So if we know we need to inspect with a low angle light on this sample, we can build a fixture that will allow that low angle light to get in there, or build a part in the machine where it's not in the fixture and we can inspect it at that point. Also, having part of the machine roll, flip the part, flip something over. If you need to inspect top and bottom, it's easiest to have, you know, clear view. Not to say that we can't solve this problem. I've had, you know, creative solutions of there was a 2-inch gap in a conveyor. We needed to see the bottom of a part. So we put a line scan camera up there with a line scan light, and we were able to see the bottom. So it's not that you can't solve these problems. It's just thinking about it ahead of time, deciding, do we want to do a line scan light, or should we build in flipping over, rolling the part, making the conveyor not too tall that we're cutting off the part that we can't see what we want to see. Just small things like that. A good way to kind of, you know, wrap up and describe what we're doing is looking at a vials application, finding the defects on these vials. Anything that appears in the green box in this image, it's going to be pretty easy to see if there's a defect in the glass. A collimated backlight will show the defect really well. But does that mean that there are no defects in this bottle based on this image? No, because anything that occurs perfectly on the edge there in those red rectangles, we won't be able to see. So at this point, do we put multiple cameras to get multiple views? Do we spin the part? Is the conveyor, you know, down enough that we can see the whole bottle? That's just things. So even an application that's as simple as seeing defects in glass, which is pretty straightforward, still has things to think about and work through to make it, that can make it harder than it really should be. Okay, next misconception is one system can perform any and every inspection and I won't have to compromise. This essentially comes down to a bad project scope. The first thing being you're trying to incorporate too many difficult inspections in one camera. The quantity isn't always the problem. You know, if I'm looking at a label and I want to read this barcode, I want to make sure the label's straight, I want to read the OCR code and make sure this piece is present. If your field of view is pretty small and everything's pretty obvious, that's very easy to do. But if we're looking at a larger field of view, a tiny OCR code is up here, tiny barcode is down here, the presence absence thing is a little bit hard to see. It just makes trying to do that all with one camera significantly harder. And so at that point, you know, maybe the question is to split it up. One looking at the OCR code, one camera looking at the barcode, making it just a little bit simpler on yourself. So a big thing is to not try and do too much with one, break it up if it needs to be broken up, and just have the cameras talk to each other through the PLC. Going hand in hand with that is inspecting the entire workpiece in one image. And this is kind of talking about a large field of view. If you're doing a large field of view and it's pretty obvious presence absence, you can get a long floodlight to flood the area, good to go. It's not necessarily a problem. That's not what I'm talking about. What I'm talking about is the applications that require kind of high precision lighting, but are a large field of view. Most of our high precision lights max out at about 300 millimeters. That would be the coaxial light. And then your light or your field of view needs to be even smaller than that. So if you're trying to do an inspection on a 500 millimeter field of view, but you require a coaxial light, it's just not going to be possible. You have to have another solution. And maybe that's indexing the camera. We'll get to that, stuff like that. The other problem that can come with having everything in one image is having too many samples within one image. In this example here, we're looking at bullets in a tray, and we want to inspect the top of the bullets. Everything that's in the center here, laser point, everything that's in the center here is looking at the top, and you can see it fairly well. As we get to the edges, we're using a short focal length lens. We can see down the side, like I talked about before, and we're not getting, you know, the same type of image we are on this bullet. Also, the stability of the fixturing will come in contact. If the holes that the bullets are sitting in are bigger, the bullet could be leaning off to one side in every image, making it a less consistent image every time, a little bit harder to program. So With all this being said, if you did want to use maybe a telecentric lens to make sure you're looking at the top of each bullet, that would work. But if your field of view is too large, your telecentric lens has to be the same size as your field of view. So if you have a 300 millimeter field of view, you have a 300 millimeter telecentric lens. That's probably not going to fit in your machine. It's going to cost a lot. Probably not worth it. So maybe this is where we look at just a 2x2, index the part, add multiple cameras, something like that. But trying to do too much with too little resources is always going to be a problem. And last but not least is 100% inspection of samples with a variety of changes and curves. And I mean this in actually two ways. So first, I mean 100% by we need to inspect 100% of our samples, and we need to have 100% accuracy all the time. That's honestly not really feasible in every machine vision application. You can get 97, 95, 99, that's still acceptable, but understand that it's not always going to be 100%. Machine vision isn't perfect. Sometimes it can. I'm not saying it's impossible, but it's not what happens all the time. What I also mean, the other part of that, is 100% inspection of your sample that has workpiece images. So when you have a workpiece that has a lot of height changes to it, it's really, really hard to find a light that will illuminate every area of it enough to see the scratches. A common application where we see this is looking for scratches on a metal workpiece. It's, usually those are pretty large, but even if they're small, the principle still applies, that difficulty still is there. So I'm going to step through why this is so hard, because it kind of comes up, and when I was doing sales a lot, it came up a lot of people saying, I want to inspect this canoe for, scratches on it. It was this giant canoe that had turns, and I had this conversation a lot of explaining why it was so hard to do that. So if we look at a piece like this, everything we want to inspect that's a flat surface, honestly, pretty easy. We get a FELux flat dome light, and it's going to be pretty easy to see everything that's flat. Where we're going to have problems is the areas that have these height changes. So those long diagonal pieces, those circles on the edges, and then the raised height changes at the bottom. If I look at the portfolio of this, and I add a camera and a flat dome light, super easy to do the flat. The light's going to shine down, it's going to reflect off my flat surface and back up into my camera. If there's a scratch, that scratch will diffuse the light, so that light won't reach my camera, it will appear darker. Scratch detected, easy peasy. Really quick tangent. I'm going to kind of take this moment to talk about why flat dome lights and coaxial lights should be about 2 times the size of the field of view. And that's the reason, is we want full coverage of the entire piece, which means we have to have an angle where the light hits the outer edge of our piece, and that same angle can reflect it into the camera. And the more reflective your piece is, the larger that angle needs to be, because you're not diffusing that light. Good rule of thumb is 2 times the size. So if you're thinking we need a flat dome light, how big does it have to be? Double your field of view, make sure you have that room. If you can go smaller for, maybe your part's a little bit more diffused, it diffuses the light a little bit better, or you have a shorter working distance, something like that, good for you. But to make sure you have enough room, assume double and go from there. Anyway, back to how the light is reflecting on our sample. So it comes down, and when it hits the angle of those raised portions, that light is reflected away from our camera, and it's not going to reach the camera. So in our image, anything that's got that height change is going to appear dark. We'll have no idea if there's a scratch there. Same thing goes for anything that's, indented or depressed on that metal stamped part. So what do? Add a light. Have a light shine on every angle that we can. Just keep adding lights until every piece of the part is illuminated. And eventually we get something like this, kind of best case scenario. A light shining on every raised edge. On top of the flat dome light, maybe there's 2 inspections, maybe they don't interfere. Either way, the part's illuminated, we're inspecting it. Now we have our next part come through, and it's not built for that part at all. So we've only able to build one inspection system for one kind of machine. So in this scenario, what happens? A lot of times the scope has to be reduced. Either we say, okay, this part A is our problem piece, we'll build it for this, and we'll 100% inspect A, we'll figure out B, C, and D down the line. Or we say, we'll just do a flat dome light, we'll only inspect the flat surfaces. If there's a scratch on the curve, we'll sort that out later. Or you build a robot and have a robot scan your item. There's pros and cons to each one. A robot scanning each piece, a lot of programming, fair amount of cost and time If you have a new piece, you have to build a whole new robot program. It'll take time, it'll take knowledge, I guess. Versus the other options, A and B, you're just not inspecting as many of your parts that you probably want to inspect. So this is more just to get an understanding of why these applications are so hard to do and why there's usually not doable. Another misconception, if we are inspecting for this, can we inspect for that too? This definitely came up the most when I would be in sales meetings. It would be me talking to somebody who brought me in. They say, hey, I've got this product, it's causing problems down the line. Can your vision system inspect for A, B, and C? In this meeting, they'll bring in other people who are maybe related to this product, but not the exact issue, but they're involved just to be important. And they'll say, well, hey, if we're doing A, B, and C, let's add D and E, because that will help us even further down the line than that. And then we say, okay, D is easy to add, E might complicate it. And then there's a third person in this meeting who's kind of the same, included, but not super related. And they say, well, if we're doing D and E, let's add F and G, and then we can do everything, and then this is great. And now this application that was, hey, we're just looking at these two things, it's going to be pretty simple, is this long grocery list. And then if we can't do that, it's like, well, if we can't do that, it's not really worth it. We just won't do the project altogether. And this initial problem we needed to solve doesn't happen. So essentially, the more that we add to our list, the less likely it is to be justifiable. And I'm not saying don't add things to your list. I'm not saying don't ask if it's possible. What I'm saying is this project will go forward if we can do A, B, C, and D. If we can do that, we will move forward with the project. If we can add E and F and G, I don't know if I'm even saying the alphabet right anymore, but if we can add that, we will. And if it's easy to do or it's just one more camera, it's not so bad. But don't let that be what derails what should be a successful and easy project, an achievable project that will solve at least some problems that we have down the line. Okay. Another misconception, this part of my design isn't relevant to the vision system, so I don't need to share this information. This relates a lot back to the first scenario I went through. We proposed a solution, hey, that doesn't fit, and we have to do it again. We have this application evaluation form. If you want us to solve an application for you, this is the information that we ask for. And it's pretty simple what it wants. There we go. It's pretty simple what it's asking for. It just wants to know, what is your part? How does your part change? What are we looking for? How is it presented to the camera? Is it through a 2-inch conveyor gap, or is it an easy peasy, we have all the room? And we want to know what camera you're using, lens, because we want to recreate your setup as best we can. So when we recommend a solution, there's no surprises of saying, hey, this won't work for this reason. And what we ask for at the end is if there's any restrictions in the light size, the light working distance, what it can be, where it can be, the wavelength it can be, something like that. And the more you share, the more we know, the more we can factor that in. So even if you think it's probably not relevant, honestly, tell us anyway. I'd rather have more information than not. Kind of my story for this one is I had one application where I was looking at a Ford flatbed truck, and it was a huge one. And I was trying to move it around the office, and they said they were using a 12 megapixel camera and this lens. So I'm climbing up, trying to mount it on stuff, and it just wasn't working. I couldn't see the defects. The resolution wasn't great. And finally I called them after an hour, and I was like, I don't know how you're solving this. I can't do it in my lab. I can come there, we can go from there. And he said, oh, no, we have 4 cameras looking at this flatbed. I was like, oh, that would have been really nice to know. Thank you. I'll move forward with that information. And, all was fine. I wasted an hour. It's not like I've never wasted an hour before. But once I had that information, I could move forward and solve the application. All was well. So it's just kind of let us know, be super clear, makes it easier for everybody when we don't have to come up with a solution twice. Okay. When I practiced this, I think I was pacing myself better. I'm a little jumpy here. Next, we don't need to test with the actual sample. So this one came from application testing, and what I'm going to focus on is the samples that you provide and how you provide them. We want good and bad samples. If you don't give me a bad sample, I have no idea if I can, find a bad defect. But not only that, we want multiple kinds of good and bad. If you send me one good sample, one bad sample, I guarantee you I can, find a way to prove that this one's bad, and that's easy peasy. But what I want to know is where that line is. Can I find the almost good ones and say that they're good? Can I see the almost bad ones and say that they're bad? I need to know what my solution can and cannot detect if it's sufficient enough. So the more that you send us, the better it is. Also, if there are multiple kinds of defects, a lot of times they say we get, 6 defects that can occur. I've sent you 3 of them. That's wonderful. I can tell you I can solve 3 of your 6 defects. And so in order for me to know my solution is exactly what you need, I need to know I can solve 6 of those defects. Another thing is not providing the actual sample or the samples as they will be inspected. Kind of story for this, we had one situation where it was our customer had a customer that had given them a sample to test. They needed to find the contrast in an image. And the sample that they had received had been sitting on the customer's desk for a few months. When they tested the sample, it was great, super easy, honestly, just a bar light, and they were good to go. And we kind of get a frantic call a few months later saying, we recommended a product to our customer. It's not working. Their delivery window's in a week, and the vision system is the biggest problem. We can't solve it. I don't know what happened. And what ended up kind of being the problem was that sample that had sat on, the end user's desk for months had changed color over time. And so it made that contrast significantly easier to see. And then when they implemented it on the actual machine, it was bright and shiny. And so it was what they wanted to see, was bright and shiny. And then we had a whole kind of problem. It ended up being fine. I think they missed their delivery window by a few weeks, but they got it out. We found a solution, all was well. But, sometimes you make sure is my sample going to change over time? If I send them an old sample, how will that be a problem? Also, sometimes people kind of call us and say, hey, we're inspecting this. Can you just go to Target and buy that and inspect that? And I'm like, well, I can tell you that the thing I bought at Target will work, but I don't know if your thing has a weird film or a weird color that will reflect my light. So take this solution with a grain of salt at that point. Not to say this can't happen, sometimes it does work just fine, but always keep in mind some things could change that just make the solution not as good for your specific part. A little bit of bonus testing advice, kind of when you're sending in the samples for us. The way you label your sample will make our job either significantly easier or significantly harder. If you just send me samples that aren't labeled good or bad, or this one just says bad and that's all I get, I don't know what's bad about the sample. I don't know if it's the shape. I don't know if it's a slight dirt. I don't know if it's the, code. I have zero idea. So letting us know, hey, this is good, this is bad, or which defect we're seeing. If you were going to do best case scenario for me, for somebody sending samples, I would say have a bag of good, a bag of bad. Each bag is its own, this is 1 defect, this is 2, this is 3. And then a little spreadsheet of part 1A, defect top right corner, flash, part 1B, defect top bottom corner, short. And going down the line, this one has a scratch in this spot. And that just helps us keep our defects organized. It helps us know what we're looking for in each sample, so we're not oh, I think I solved this, which happens sometimes too. And also I have this picture here. Try not to mark the parts where the defects that we're inspecting, circling, hey, look, that's what we want to see, makes it really obvious, and that's nice. But I don't really and this is maybe just a personal grievance of mine, easily could be that, but I don't really like having to say, okay, if the marker's not there, it should still probably work, kind of thing. So, labeling your defects makes everybody's job, aka mine, easier. Okay, another misconception, knowing the light's lux or lumens will tell me if it is bright enough. When people say, hey, we've got to reach this, exposure, what light do you recommend? What's your bright light? I can't do that. I can't just say, yep, this light's 700,000 lux, go for it. And that's because the light irradiance will change over your working distance. The closer I am to the part, the brighter it's going to be. Further away I get, the darker it's going to be. And I don't know exactly what that number is. Also, the way your part is, if it's really dark, it will absorb more light. If it's really bright, it will reflect more light. So I don't have a good way of knowing exactly that it will work. Also, the way it, reflects will change with a different light working distance. As we're super close, we get a really big hot spot in the middle. It's pretty narrow. And as we move away, that spreads out. That hot spot is less intense. And so what we would do in this scenario is we would say, okay, based on what you're looking at, I think you need a, flat dome light. I'm going to send you the flat dome light and you test it, make sure that it's the right wavelength, the right size, the right solution. And then we'll talk about the intensity. So they say, okay, great, this light works. I need the exposure time to be 100 microseconds. In order to get the image I need, I had to put it at 400 microseconds. And say, okay, now I know I need a light that's 4 times brighter than the standard light. So I can say, okay, we can try a Gardasoft controller, overdriving it 4 times. That might be enough. Won't give you really any room to grow if you, eventually shorten your exposure time. Maybe you want to consider a PF series, which is that extra bright one. And then we go from there and we use that light instead. So I can't just say this light is bright enough, happy times. There's testing that needs to be involved to make sure that it's right. Okay, if that application, if it works for that application, it will work for me. And this happens a lot. People call in and say, hey, I'm doing a ramen inspection packet. Can you just, have you done something like this in the past? What did you use? Whatever. And I'll say, yeah, in the past, we've done similar things. A flat dome light with a polarizer was success. I am happy to have those conversations. I will have those conversations with you every day if you need to have them. What I don't want is that being, okay, great, I will purchase that and not think about it. And the reason why is because there are things I might not know about your application that would change my answer. For this example, the ramen packet, this is what we used, a flat dome light with a polarizer. And it was great for all of the flavors to make sure it was the right flavor until I got to the shrimp at a 45-degree angle. Unbeknownst to me, I would have no way of knowing this. This specific material, when 45 degrees to the polarizer, doesn't have the polarizing effect. I've seen this before, Scotch tape, oddly enough, same thing. Super odd, no way of predicting it. And so if the customer had just purchased on my recommendation, installed it, inevitably this configuration would come down the line. Their customer would say, what the heck, now I can't inspect anytime this happens, I don't get the information, we need something else. So even if it's a simple answer, that means it's a simple test, just test it. Just make sure it works and there's not going to be a problem that you didn't expect. Just because it worked last time, if it's a different application, there might be something you just don't know. Okay. I can buy the same hardware for every application. This definitely came into play when I was talking to OEMs a lot who were doing the same thing over and over again. And if you're doing the same app, building the same machine, obviously do that. But if you have a lot of different applications coming up, more machine builder type, you can't just stock 16 millimeter lens, 2 megapixel camera, and a white ring light. I do understand that filtering on the machine vision camera side has gotten really good. I've seen it solve applications that it really shouldn't have been able to solve, and AI is really going to change this game as well. That being said, in the times that we're in, my whole shtick is a machine vision light can make or break an application. So if we had one light that we stocked in 4 different applications, could it solve all of them? This bottle, sure. Even the barcode, sure, depending on what we want. On the rest of them, yeah, maybe. And then a ring light, here's kind of what we would get. If we only stocked a dome light, here's what we would get. So if we're comparing these samples with the lights that we have, if we had a bar light, we could easily solve this application. But if we only stocked a dome light, this would be really hard. Then if the next application that came was a cap, dome light would be perfect. We nailed it. How great. Honestly, even the other applications, put a polarizer on that ring light, you could still solve it. So that's not the worst thing. Looking at a circuit board, if you're trying to see the contrast in the numbers, a bar light would be good. If you're trying to see the solder, though, the quality of the solder, you would want probably more like that flat dome light. And then if you're looking at the metal part and you want to see that little rust spot right there, ring light could be fine, 2 bar lights, but a dome light's going to be your best answer. So essentially, if you have already tested the application, you've already done it before, the ring light works, buy the ring light. But if you have a lot of applications that can come through, make sure you have a good vision lab, or you're reaching out to your customers or us and saying, can I borrow this light to test this application? We're getting to the end here. If I can see the defect, a camera can inspect it. And this is a big, I think people are coming to terms of learning that this isn't always the case, but what we end up seeing is, for example, a bruise on an apple. We look at the bruise, a camera takes a picture of the apple, our brain processes it, the camera's processing system interprets the image, and we make assumptions. Our brain says a green apple, a bruise on an apple. A processing system, a camera, says green apple, and it sees discoloration on an apple. Is it a brown bruise? Is it the brown discoloration that some apples can have? I can't tell you. All I can see is discoloration. So it's really hard to draw that line of this brown is bruise, but this brown is okay. It can't really make that determination. AI is, like I said, going to change the game. It's going to probably make that a little bit more gray on what it can and can't do. But right now, this is kind of where we're at, or most people are at, I would say. So just because you can see a defect, if I hold it at the right light, I can see this, whatever, doesn't mean that the vision system has the processing power, the context clues that it's going to need to make the right determination. That defect or that discoloration is good, that discoloration is bad. If you want more information on kind of the theory of light and color, the relationship between human vision and machine vision, our headquarters in Japan is releasing a honestly very deep technical guide into just the relationship of light and color and kind of how LEDs came about and stuff like that. Me and my counterpart are doing she's doing a lot of the translation and I'm doing a lot of the technical checks. I've read them all. They're dry but informative, if I'm being honest. But they release a chapter a month, and it's an interesting read if you're interested on just learning more kind of about that topic. It's on the CCS group website, Theory, Light, and Color. Okay, so that's the end of all the misconceptions that I have. In the end, after making this presentation, I realized it was kind of just me letting out my grievances that have built up over the years. So thanks for listening to those. But what do I want you to know? What are we taking away here? First, we're taking away, consider vision at the beginning as early as you can. We want clearance. We want to have the flexibility and the freedom to solve our machine vision system the way it needs to be solved. The more restrictions you have, the harder it is to get the outcome that we want. Narrow your scope to an achievable outcome. Either, take this complicated thing and simplify it with more cameras, or, cut out what needs to be cut out to just say, okay, we can't do everything, but at least we can do this, and at least that will help more than doing nothing. Test with the actual samples, good and bad. All the defects that you can get your hands on, send us those too, test with those. Make sure that your system can really solve the application as best you can. Test every application. I think that was a common theme throughout. Every time I would say something, I always ended up with just test it. Do this, test it. So just, even if it's an easy test, or if it's an easy solution, it's probably going to be an easy test then. And don't assume an inspection will work just because you can see the defect with your eyes. AI might change that in a few years, but right now, test it. Okay, that's all I got for you guys today. My name again, Lindsey Sullivan. You can reach me at that email address or phone number. Al Fabian is our sales guy for you, everyone in Minnesota. He'll be at our booth back there with all our lights. So if you have questions, come find me. Otherwise, sales@CCS America is a good email address to just kind of get a hold of anybody. And don't call me after September.